This is lecture 11F, and it is on the Taylor series. In a later lecture, I will derive the Taylor series, but this derivation is not used to construct the Taylor series. So here, I'm going to go through the steps of constructing the Taylor series and some rationale that leads up to it. Okay. So what I'm going to do is start with the power series. It's shown right here. Here's a power series. So there's some constants, coefficient c to the n times x minus x naught to the n, and that will be the power series about x naught. Now we know that the power series converges at least one point, x equal x naught. It might also converge in a radius about x naught. It might also converge everywhere, but at least it converges at one point. We also know the power series can be differentiated. So from these two conclusions, we can make a correspondence between those coefficients c to the n, which we have to evaluate in order to make this power series represent some particular function. So we need to give some forms to c to the n, some values to c to the n, and we end up making a correspondence between these coefficients and the derivative of the function at x naught. Once we get done constructing the Taylor series, we still have two questions. What is the interval of convergence? If this only converges at one point, that's really not of much use to us. Okay. But we will have the scenario that we do for power series, because this is in effect a power series. It will either converge at one point, x naught, converge in some interval about x naught, or it will converge for all x, which is, of course, the ideal situation. Now, when we go to apply the Taylor series, obviously we can't sum up an infinite number of terms every time we want to evaluate the function at, say, 2 or 10. So we're going to add up a finite number of terms. What is the error associated with adding up only a certain number of terms? I mean, how far off are we going to be if we use 10 terms, or should we use 100 terms, or use 1,000 terms? We want to be able to know these answers to these questions. Now, the answers to both questions are given by a term that's called the remainder. Well, let's first develop this correspondence between the derivatives and the coefficients. So we're going to start off by letting f of x be a differentiable function. Okay. And we assume it has derivatives of all orders, and that it's represented by some power series. Okay. Now, if we evaluate this power series at x equal x naught, then, well, first let's expand this. In the first term, when n is 0, we have only the constant c naught. After that, c1 times x naught, x minus x naught. Let me fix that. No fixing is needed. I'm showing it evaluated at x naught. This term would actually be, let me write this out instead. This will work better. Okay, if I just expand this right here, the first term is going to be c naught. The next term is going to be c1 times x minus x naught. The next term is going to be c2 times x minus x naught squared, and so forth. Okay, there's a plus sign. Now I'm going to evaluate at x naught. When I evaluate at x naught, this term right here becomes x naught minus x naught. In other words, 0. This term is 0, and I'm left only with c naught. In other words, the coefficient c naught, the first coefficient, is equal to the function at x naught. Now let's take the first derivative. If I take the first derivative of this, let me get the pen. If I take the derivative of the power series, remember we can do term-wise differentiation. When we do that, the first term is 0 because it didn't depend on x anyway. C naught, it was just c naught, constant. The second term, if I'm going to write up here what the power series is so you can see. c1 times x minus x naught. The second term, or third term here, is c2 times x minus x naught squared. Okay. This is the power series before differentiation. Now let's differentiate it. Okay, if I take the derivative of a constant, I get 0. That's the first term. If I take the derivative of the second term here, I will get just c1 by itself. If I take the derivative of this third term using the power rule, the 2 comes out in front, so I have 2c2 times x minus x naught. The next one will be 3 times c3 x minus x naught squared, etc. Okay. Now evaluate at x equal x naught, and you'll see that the only remaining term is this c1. The rest of them vanish. So the first derivative of the function at x naught equals c1. Let's take another derivative. Okay, when I take the second derivative, I will have 2 times c2 from this right here. But here I had 3c3 times x minus x naught squared. Taking the derivative gives me 3 times 2 times c3 times x minus x naught, and so forth. When I evaluate at x naught, I end up with 2c2. So twice c2 equals the second derivative. Now let's take the third derivative, and by taking the third derivative and evaluating at x naught, we find that the 3 times 2 times c3 equals the second derivative. And we can keep going in this fashion, and we get the general result that the nth derivative equals n factorial times c to the n, which is the nth coefficient of the power series. Now we're going to use all those results and turn them around to solve for the coefficients. So here we are. In this case, we've listed the coefficients here, and this is the result. So in general, c to the n equals the nth derivative of the function divided by n factorial. We can substitute these expressions for the coefficients into this power series and get the Taylor series. So the value of the function f of x equals the function at x naught, remember that was the c naught term, plus the first derivative times x minus x naught, plus the second derivative evaluated at x naught divided by 2 factorial times x minus x naught squared, etc., etc. The nth term is the nth derivative evaluated at x naught divided by n factorial times x minus x naught to the nth power. It's easy to remember because it's the nth derivative is divided by n factorial, and x minus x naught is raised to the nth power. Here there's a 2, and a 2, so it's not too hard to remember, and that is the Taylor series. So here we're going to construct a Taylor series. We're going to let f of x be the sine of x right here, and we're going to construct about x naught equal to 0. All right, a little terminology. In many math books, they go out of their way to call a Taylor series about 0 as the Maclaurin series. You can use that terminology. I'm much more familiar with just saying the Taylor series about 0 and not giving it the other name. I guess it doesn't give honor to the person who did some development of it, but it's more common just to say the Taylor series about x naught equals 0, or about x equals 0. Okay, so first thing I'll do is I'll take all the derivatives of f that I want and evaluate them at x naught, because I'm going to use those to find forms for the coefficient, or values for the coefficient in this case. So here's the function, here's the first derivative, second derivative, third derivative, evaluating all of them at x naught. I end up with this, the zeros and the ones here, because I end up with cosines or sines, plus or minus cosine or plus or minus sine. And evaluating at 0, I either get 0, plus 1, or minus 1. Now we can find values for the coefficients. C naught is the function at x naught, which is 0. C1 is the first derivative, becomes 1. C2 is 0. C3 is the second derivative, or the third derivative divided by 3 factorial. It's minus 1 over 3 factorial. C to the fourth is 0. C to the fifth is the fifth derivative at x naught divided by 5 factorial. That becomes plus 1 over 5 factorial. Then we have a 0. Then we have a minus 1 over 7 factorial. Let's put it all together. And here's the result. This will be the Taylor series for sine of x. Okay, here's the 0. This next coefficient is 1. The next coefficient is 0. Then minus 1 over 3 factorial. Another 0. 1 over 5 factorial. Another 0. Minus 1 over 7 factorial. And when I work all this out, remember x naught was 0, so I put the 0 in here just so you can see it. Of course, it's going to vanish. And when I work all this out, of course, not bothering to write the zeros, I have the sine of x, the Taylor series for the sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. I can write that in sigma notation. It is the sum from n equals 0 to, well, in this case I'm using the n, just saying in terms, 2n plus 1 factorial minus 1 to the n times x to the 2n plus 1. So this is a compact form. Generally, you can just think of it this way. Notice that it's odd. Well, that makes sense since sine is an odd function. Up to this point, we can only assume that this Taylor expansion is valid, converges at x naught. Well, that's only one point. Of course, we would like to have a slightly larger radius of convergence for it to be useful at all. Okay, so remember, it was an infinite series. What I showed before was a finite series, but let's go ahead and think of it as an infinite series now, and we could break it into two pieces. We could break it into a partial sum. For example, here, here's the Taylor series. S2, here's a pen. S2 would be the sum of the first two terms, and then you would have a remainder associated with only using two terms. Or if I used 40 terms, here I added up the first 40 terms of my Taylor series, then I would have a remainder associated with using only 40 terms of the Taylor series. Now, as I mentioned in this notation alert here, there are two capital R's going around. One is a radius of curvature for convenience, a radius of curvature, radius of convergence, and it's written with no subscript. The other is the remainder from the nth partial sum, and that is written with a subscript. The subscript tells you how many terms you actually added up. Right? And the rest, of course, you neglected since you can't add an infinite number of terms. So these are the remainders, what are shown here with the blue underlining them. As I mentioned before, this remainder, r to the n, will provide two answers. It will give the radius of convergence, and it will also give an estimate for the error of using only in term. So here's the Taylor series evaluated some x in an interval about x naught. So I'm just going to write out the Taylor series again. The remainder, in terms of the derivative of the function, is written like this. There's another lecture in which I derive this. Right. But this is what the remainder is when I work it out. It is the next derivative, f to the nth plus 1, evaluated at some c, right, divided by n plus 1 factorial times x minus x naught to the n plus 1. Right. And the c lies between x naught and x. X is the place you want to evaluate the function. X naught is where the series was expanded, the point where this about which the series was expanded. So we're just going to use this remainder here. In another lecture, like I say, I derive it. And here's the important point. If this remainder converges to 0 as n goes to infinity, then the Taylor series also converges. On the other hand, if there, I don't know what I wrote there. Oh, I see. Okay, now I know what I was trying to say. Sorry about that. If the remainder converges to 0 as n goes to infinity, then the Taylor series converges. And you can look at it another way, where for the value of x at which the remainder converges to 0, the Taylor series also converges. If the remainder converges to 0 for any value of x, then the Taylor series converges everywhere. If that remainder only converges in some radius about x naught, then the Taylor series only converges within that radius as well. So let's look at an example here. We have the Taylor series of e to the x about x naught, and I'm just going to write it out here without deriving it. I'm sure you've derived this before. Or if not, you can look in the back of the book or look at the lecture on useful Taylor series, and I present this one. E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Right. So if I use so many terms, I use n terms, I will get an nth partial sum, and the remainder is all here. Remember, it was the derivative evaluated at c. Well, what's the derivative of e to the x but e to the x? So that's e evaluated at c divided by n plus 1 factorial times x raised to the n plus 1 power. Right. What happens to this? The limit of this remainder, in the limit, if we take the limit as n goes to infinity of this remainder, we have e to the c, which is a constant, times n plus 1 factorial times x to the n plus 1. All right, and now we're going to have this. Here's what we have that we need to take the limit of: x to the n plus 1 over x over n plus 1, and we know that limit is 0 from the useful series lecture. So this is true for all x. Therefore, the Taylor series converges to e to the x everywhere. The second use of this remainder is to figure out potential error. So let's just look at this for a few minutes. And let me get the marker here. Okay, here is the remainder. And it depends on x minus x naught. So x naught is the point about which you expanded the Taylor series, and x is the point where you're trying to find the value of the function. Well, the greater this difference, this is raised to the n plus 1 power, the greater the difference, the greater the value of r. So, there we go. The remainder depends on the distance from the point of expansion x naught. Right. The next thing to note is that it is raised to this n plus 1 power, and it depends on the number of terms used. The more terms used, the smaller the error. Well, assuming convergence here. Okay. All right. The derivative of the function, the n plus first derivative of this function. Remember, this function has derivatives of all orders, so it is bounded, and it will be less than or equal to some m. Okay, it has some upper bound. So if we use that upper bound, we can now estimate the error as the greatest value of the n plus 1 derivative in the interval x to x naught times x minus x naught to the n plus 1 over n plus 1 factorial. Let's go back and apply this to the Taylor series for the sine of x. All right. Here would have been, if we remember, we're using only those odd powers, so the counter looks a little bit different. Get the highlighter here. Okay, here's the error function, and again, we just don't have r to the n. We're using r to the 2k plus 1 because that sort of reflects that particular function. We have x raised to the 2k plus 2 divided by 2k plus 2 factorial. Okay, this was the one that depends on how far you are from the point at which you expanded, and in this case, we expanded about x equals 0. So it's how far away from 0 you're trying to evaluate the function. Then it was one of the higher order derivatives of the sine of x, evaluated at x equals c, NEC. Well, note that the derivatives of sine x are either plus or minus sine x or plus or minus cosine x. And they are all less than or equal to 1. The greatest value that they're going to have is 1. That's the upper bound. That's what we'll pick as the m. So that simplifies the calculation. These are all bounded by 1. So the remainder is going to be less than or equal to, actually, x, absolute value of x, raised to the 2k plus 2 power divided by 2k plus 2 factorial. That's the remainder. Now let's evaluate this at a couple places to find the error. So let's look at x equal 2 pi. We want to evaluate sine. So what we have is this situation. We have the sine of x, and we're going to evaluate it by taking so many terms in terms of the sine function of the, I'm sorry, this will be in terms of the Taylor expansion. Okay, and there'll be plus this remainder. Right. If we're only using this much, of course, then we would say the sine of x minus this Taylor's expansion, the nth, using the first n terms, the difference is going to be this remainder. So the remainder is the error between taking all, between actually evaluating the function, knowing the value of the function, subtracting that from the nth order Taylor expansion. Okay, just taking n terms. I've only said that 20 times, so I'm sure I probably didn't say it right any of the times. All right, so let's look at what r to the n is. So let's say we take 21 terms, and we want to evaluate the function at 2 pi. All right, so we can substitute that in from the expression we had before. It'd be 2 pi to the 22nd power divided by 22 factorial. That gives an error of 0.000323, which doesn't seem too bad. Now let's use the same number of terms and find out what error we get if we evaluate at 4 pi. Well, obviously that is a pretty horrible error. It isn't upper bound on the error, but still, that's pretty large. And if you recall what these expansions look like, let me erase this for a minute. Get a line. Okay, now I have a sine wave here. It's 2 pi, it's 4 pi. Okay, I'm just going to look at this much of it. Oh, and when I expand about x equals 0, then I get good agreement right in through here. Okay, right in through here. So if I did a linear expansion, I'd have good agreement, but only at x equal x naught. As I take more curves, as I take more terms, then it will follow the curve. For example, it might follow it to here and then start breaking away. Might follow it to here and then start breaking away. This might be, say, 5 terms. Right. And if I add more terms, then I might follow it further, like, say, to this point. And then it might, well, I drew it up, but it's not necessarily true that it goes up every time. Okay. This might follow it to here. You'll see the same thing reflected on both sides. But at any rate, what you see is you see good agreement for values of x from x naught, say to a certain, a certain value here by using this many terms. After that, the agreement between the Taylor, this case would be a 5 fifth order Taylor expansion, and the actual values of the sine of x gets very, very bad. And that's what you see here. It would have real good agreement for 21 terms all the way out here to this point. Pretty good agreement. And then when you try to look at the difference between this function and the function here at 4 pi, of course can't draw it in the same graph the way I've done it, you'll see a very big error. So in this later lecture on the derivation of the Taylor series, I show you exactly how to derive this error, the expression for the error, for the remainder.